Okay, salam and good morning. So today our group will present a project which is design improvement and analysis of aircraft engine bracket. So our group member is Bradley O'Neill Bond, and myself, Randy Sarah Petrus, and lastly Tang Tek Hen. So we are from program UR65210004 from project design, and this project is for the courses MMK 21103 computer aided design. So for introduction for this project, the aircraft engine brackets support engine cooling during maintenance and must handle high load without failure, while staying lightweight to reduce fuel use and emissions. So the problem statement from the original bracket is that the material used is titanium, which is heavy 2.05 kilogram, and it has high energy consumption, which is 361 megajoule per kg. So the goals for this project is to redesign the bracket, and our chosen material is beryllium, and because it has lighter, greener, and more efficient solution.
Okay, why we use beryllium? Beryllium, it shows that lower density than titanium. It is 1,840 kilogram per meter cube, and titanium is 4,430 kilogram per meter cube. Beryllium is 60% lighter than titanium. And compared with stiffness, beryllium is more stiff than titanium, which is 287 gigapascal, bigger than 113 gigapascal. Beryllium is 2.5 times stiffer than titanium, so it will cause less deformation. For the thermal expansion, beryllium also higher than titanium, which is 11.3 times 10 power negative 6 per degree Celsius, higher than 8.6 times 10 power negative 6 per degree Celsius. Beryllium shows a more comparable stability. The production energy means that beryllium has a lower production energy than titanium, because beryllium needs lower energy to produce than titanium. Titanium needs 361 megajoule per kilogram, 15 times of steel. Okay, next. Our objective is substitute titanium with better material, which is lighter and sustainable. And we need to meet the mass lower than 0.8 kilogram, and the FOS is between 1.2 to 3.0. And the deflection target is lower than 0.35 millimeters. For advanced analysis, validate design via thermal stress and vibrate test. Contribute to SDG 12 by reducing energy consumption and material waste. Eliminate fracture rates under maximum loads. The bracket was optimized by using beryllium, selected for its height stiffness to weight ratio. The main objectives were to reduce the mass, minimize the deformation, and increase the safety margin under static loading. The geometry also of the bracket was carefully designed to ensure the efficient of load distribution and also to lower the stress concentration, especially at fillets and mounting points. Even with reduced material usage, the structure still maintained excellent strength with stiffness. It was a lightweight without compromising performance. Next. The tree diagram shows that we designed three different designs of aircraft engine bracket. Next. The table shows about the comparison between the three design. The present design one shows the shows the mass of 0.57832 kilogram, and the present design shows the lightest mass of between three design, which is 0.57724 kilogram, and the present design tree shows the highest and the heaviest mass among three design, which is 0.75107 kilogram. The FOS which is factor of safety. The present design one shows the lowest factor of safety, which is 1.20539, and the design two, it shows the most factor of safety, which is 1.3713, and the design three is 1.2874. The total deflection of design one also have presented highest total deflection on it, which is 0.066927 millimeters. And also, the present two shows the lowest total deflection, which is 0.0432747 millimeters. And the design three is 0.062546 millimeters. The conclusion is present design two perform the best and showing the lowest stress of total deformations with a high factor of safety. Why is more safety because the key or factor influencing in performance included smooth geometry and reinforcement to lower the stress, the material stiffness, and optimize thickness for strength. We also use the realistic loading of boundary condition in the analysis. These choices lead the lightweight yet strong bracket suitable for static loads.
This is the thermal stress analysis where we test it for with thermal and without thermal. So the key finding here is the without the thermal, it was the model. Our model was safe, the bracket, where the room temperature was 22 degrees Celsius, and without the thermal, the FOS of the bracket is 1.37, and the stress was 204 megapascal. But with the thermal, it was at the critical failure, where the temperature was 300 degrees Celsius, and the safety factor was dropped to 0.062, and the stress was increased to 4,504 megapascal. So the reason of the failure is the thermal expansion induced stress, where the fixed support prevent expansion, and the material softening at the high temperature.
So next is free vibration analysis. Free vibration analysis is used to find out how a part move or shake on its own without any outside force. In aircraft design, it is important to know the natural frequency of a part so that they do not match the engine working vibration. If they match, it can cause strong shaking known as resonance, which can damage a part in this which can damage the part. In this project, the free vibration analysis was done on the new bracket design to make sure the natural frequency are much higher than the engine vibration. So here we have the table of max deformation on 6 mode. So here we have best bending on the fillet, torsion twist on the web, lateral buckling, and thin section warping, multi-axis vibration, and high frequency distortion. So next, so here we have the top 3 with higher deformation. So here we have it on mode 1, mode 2, and mode 4. So next is we have no resonance because all frequency obtained are all greater than 10,000 Hz, far above engine vibration, which is only 275.8 Hz, and the weak area, high deformation in fillet and thin section, and mostly we can see at the red zone in the mode shape. So the solution we choose is to add rib or thicker wall to stiffen this spot.
So as the conclusion, we achieve mass reduction, structural safety, and vibration resilience, where the mass reduction we reduce 71.8% lighter than titanium, where our beryllium, our bracket was 0.577 kilogram compared to the titanium, where it was 2.05 kilogram. So it was 27.8% below the target, whereas the target must be below 0.8 kilogram. For the structural safety, our FOS was 1.37, where the target was 1.2 to 3.0. So the minimal deflection was 0.043 millimeter. It was 87 below the limit. For the vibration resilience, it was no resonance, where the lowest frequency of our bracket was 10.790 Hz versus the engine vibration, where it was 275.8 Hz. It was 3,800% safety margin. So the limitation of our bracket is thermal vulnerability. So where the thermal is 300 degrees Celsius, make it drop to 0.062 for the safety factor, where our bracket needs the thermal protection. For the lesson that we learned from this project is, we know that the beryllium excel is stiffness over waste, but require thermal management. The geometric optimization like fillet and rib is critical for the stress distribution. So that's all from us. Thank you.
This help keep the bracket safe and strong during use. The result also